Is life an amazing phenomenon exclusive to our planet? Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. However, thanks to the latest extraordinary advances in astronomy, it appears that we are closer to solving this mystery. State-of-the-art space probes explore planets and moons in our solar system, while sophisticated telescopes scan the universe looking for answers. The results of the research are amazing.
One of the big triumphs of astronomy in the last 2 decades is to show the majority of stars have planets. There are planets all over the place. There are more planets than stars.
These findings have been made possible thanks to the NASA space probe Kepler, whose launch in 2009 marked a milestone in the search for life beyond the boundaries of our solar system. We now know that in our galaxy alone, there are billions of Earth-like exoplanets. Given the vastness of the universe, with more than 100 billion galaxies, it is hard to conceive that somewhere there is no Earth-like planet that can harbor life. Finding it is simply a matter of time.
It's a game changer. It changes what we think about the possibility for life somewhere else. Exoplanets and extremophiles, 2 game changers.
This leads us to think that in apparently harsh environments in our solar system, there is now, or may have been, life. We may find some form of life in the strange methane lakes of Titan, in the oceans hidden under the mysterious icy surface of Europa, in the gigantic geysers of Enceladus, or in the desert plains of Mars.
The second genesis within the same solar system implies that life, the origin of life, is a likely event.
We don't know if the discovery of life will happen first on one of these moons or planets in our solar system, or on an Earth-like exoplanet. But what we do know is that we are closer than ever to unveiling one of the greatest mysteries of nature, whether there is life in outer space. Life, an unbelievably perfect combination of elements able to create living matter. Possibly the biggest mystery of nature. A combination of matter that shows certain attributes that include responsiveness, growth, metabolism, energy transformation, and reproduction.
We don't yet know exactly what life is. We don't have a working definition. Probably my favorite definition is that life is some sort of chemical entity that is self-enclosed and is capable of Darwinian evolution by natural selection.
Some studies state that life may have begun in Earth as early as 4.1 billion years ago. That is still only slightly younger than Earth. A question arises immediately. Is life an exclusive phenomenon of Earth? There's no easy answer to this question. The chemistry of life, begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10 to 17 million years old. life may have emerged independently at many places throughout the universe. Or life may have formed less frequently, then spread maybe by meteoroids or comets between habitable planets in a process called panspermia. In any case, complex organic molecules may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of Earth. According to these hypotheses, this process may occur outside Earth on several planets and moons of the solar system, and on planets of other stars, the so-called exoplanets. Since ancient times, humankind asked itself if we are alone in the universe, and if there is life beyond Earth. Those questions may not be easily answered. However, they have always fascinated us.
Astronomers have been interested in the question of life beyond Earth for a very long time. I mean, we can trace back through the ancient Greeks and Romans and Chinese writings speculation about life beyond Earth.
The main issue to search for life in outer space is to establish what are the life support conditions. A source of energy, such as from a nearby star, is needed to drive endothermic, or energy-absorbing reactions. Raw materials, predominantly carbon, build and form organic molecules.
So the building blocks of life on Earth, and we know that there are carbon, hydrogen, oxygen, nitrogen, and others. They are what we are looking on other planets to look for life as we know it.
These building blocks for life, at least as we understand it, are ubiquitous.
Also indispensable is the presence of a liquid or very dense gas as a solvent for biochemical reactions to occur quickly and stably. Liquid water, the life-sustaining universal solvent, at least on Earth, entails certain atmospheric composition and temperatures.
In order to have a habitable environment, you need three things. You need liquid water, and you need organic material, and you need energy. And there are a number of places in the solar system where all three of those things are thought to exist.
Now we already know the key conditions for supporting life. A question arises immediately. How many planets or moons in our solar system meet these conditions? Considering that one of the key prerequisites for extraterrestrial life is the existence of liquid water, there are three candidates in our solar system to have liquid water on its surface: the planet Mars, the Jovian moon, Europa, and the moon of Saturn, Enceladus. Besides Mars, Europa, and Enceladus, which might have liquid water on their surfaces, there is another candidate for supporting life in our solar system: Saturn's largest moon, Titan. Until 2004, Titan remained a great mystery to astronomers, as a dense, opaque haze prevented understanding of its surface. On 2004, the spacecraft Cassini reached Titan and released a small probe named Huygens. That would change everything. These are the images that the Huygens camera recorded as it descended through the haze. Titan's landscape is very similar to Earth's, with mountains, valleys and plains. When the probe touched down on the surface, it revealed something no one expected. There were pebbles everywhere, similar to the rocks of riverbeds on Earth.
When you're looking at those pebbles, yes, they are rounded pebbles and they have been rounded by torrents and rivers. But they are not rocks in the sense that we understand. They are actually water ice, so hard that it behaves like rock.
How were these rocks eroded? Is there liquid water on Titan's surface? At minus 180 degrees Celsius, water should be frozen solid. Cassini's radar had the answer. It showed us that Titan's surface has hundreds of lakes.
The big difference, though, is that they are not made of liquid water. They are made of liquid methane.
These two hydrocarbons on Earth are volatile gases. But with Titan's chilly temperatures, they are liquid.
The atmosphere of Titan has methane and ethane and other organic materials that provide a very different kind of chemistry, but a kind of chemistry that is reminiscent of what Earth very possibly looked like before life was abundant.
All these worlds are very far away from the heat of the sun, so they are extremely cold, and some of them are exposed to very high levels of radiation, as they have very thin atmospheres. Therefore, their environments are quite hostile to life. However, life might have found its way.
We also now know about extremophiles, forms of life that live in environmental conditions that when I was a student, I was told, impossible. Can't have any life there. It's too hot, it's too cold, it's too acidic, it's too basic, too much pressure, too much radiation. They have evolved to thrive in those conditions. So this whole new field of study of extremophiles, it's a game changer. It changes what we think about the possibility for life somewhere else.
Extremophiles such as bacteria that live in high temperature, toxic, deep-sea hydrothermal volcanic vents on Earth offer insight into life that could have developed on other planets that mostly share such extreme, inhospitable environments, which also can include freezing temperatures and minimal sun exposure.
This gave us such a different view of actually what was necessary for life to survive. And all of a sudden, the solar system totally exploded. The horizon of what we call habitability and habitable environment completely expanded in ways that we could not have expected at all.
The chances of finding life on any of these remote worlds in the solar system are now much higher. Finding it is simply a matter of time. Of all 160 or so planets and moons in the solar system, Mars has so far received the most interest from astrobiologists. There are many signs that show that very early in its history, Mars was much like Earth, with large areas of liquid water, a thick atmosphere, ample sources of energy for life, and a good inventory of organic molecules.
In fact, what I like to say when I compare the two planets is that you don't have to invent words to describe Mars. You have mountains, you have canyons, you have polar caps, you have dunes.
There is evidence that Mars had a warmer and wetter past. Dried up riverbeds, vast canyons blasted out by epic floods, valleys carved by raging rivers, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found.
There's a lot of evidence for liquid water earlier in the planet's history, much earlier, about 4 billion years ago, and perhaps some transient water in the time since 4 billion years ago.
But the evidence indicates that all that water disappeared from the surface billions of years ago as Mars cooled down and lost its atmosphere. Did life ever get a foothold on the planet?
As we're looking for evidence for ancient life on Mars, some people think that actually we already had some evidence of that life landing on our own planet. And the best example of that is the Allen Hill meteorites.
We had a piece of Mars here in the lab. We still have it. Allen Hill's 84001, a rock that was chipped off Mars by an impact millions of years ago, wound around in space, landed on the Earth in the Antarctic ice sheets, and during the 1984 spring collection season, as that ice was melting and those black rocks were picked up in the melt pools, we realized by the gases that are included in that piece of rock that that's a piece of Mars. And we took it apart at microscopic scales. And we had a big scientific controversy because there were scientists that were claiming features in that rock could only have been produced by biology, and other scientists saying, nope, you can get that with geology.
The search for life on the red planet started decades ago. In 1976, a search for microbial life on the red planet was performed for the first time ever. 2 decades later, in 1997, the Pathfinder mission took a new step forward in this search for life adventure. It found magnesium, aluminum, iron, and phosphate in Martian rocks, which are all possible life-supporting materials. In 2008, the Phoenix spacecraft explored Mars' North Pole. After digging a few inches, it found a white material that evaporated several days later. The analysis of that material revealed it was water ice. Satellites scanned both polar caps and found that there was a lot of water ice under a layer of frozen carbon dioxide. If all that ice ever melted, a more than 80 feet deep ocean would cover the whole planet. The same satellites also discovered that there was ice buried everywhere beneath the desert plains. That was a shocking discovery. Mars had huge amounts of water ice everywhere. But could life exist in the buried ice itself? We now know that there are extremophile microorganisms able to live in similar environments in the dry valleys in the Antarctic here on Earth.
Currently, Mars is very dry and very cold. It's like some regions in Antarctica today, and it's kind of like a very cold desert. So liquid water would not be stable. If you opened up a container of water, it would immediately evaporate because it's so dry.
Buried ice was found under a layer of dry dirt, as happens on Mars. At the point where the dirt met the ice, there was a thin film of liquid water where extremophiles thrived, just for a short time. These microorganisms remain frozen and dormant most of the year, and they only flourish for a few warm weeks during the summer.
Today, Marcus could still live at depth, at some depth, favored by the presence of thin films of water or maybe more liquid water, because the deeper you go, the more the chance that the water could be liquid.
During the Martian summer, it's common to reach 20 degrees Celsius at the equator, so the buried ice might melt and create similar conditions to those found in the Antarctic dry valleys.
Any microbes that might have been there, they're probably living within the rocks or under rock coatings. So that's one of the analog sites that my group's been investigating, is microbes that are living underneath the surface, because that might be viable for Mars as well.
A future mission could eventually prove whether this hypothesis is true or not. But there is another possibility that liquid subsurface water exists on Mars. Mars' huge volcanoes, such as Olympus Mons, could contribute internal heat to sustain subsurface water. This would imply that hydrothermal vents could exist on Mars as well, and therefore it might be also possible that extremophiles, similar to the ones that thrive in the terrestrial hydrothermal vents, might also exist on Mars. However, this is quite unlikely. Everything would change if we were able to find liquid water on the surface. On September 2015, NASA's Mars Reconnaissance Orbiter made an incredible discovery. This spacecraft provided the strongest evidence yet that liquid water flows intermittently on present-day Mars.
It's not a pure transparent water. It's very briny water, very salty water, which allows it to remain stable for a little while at the surface, because the pressure at the surface of Mars is very, very small.
Using an imaging spectrometer, researchers detected signatures of hydrated minerals on slopes where mysterious streaks were seen on the red planet. They darken and appear to flow down steep slopes during warm seasons, and then fade in cooler seasons. This finding proved what anyone could have imagined. On Mars' present-day surface, there is liquid water. Maybe in some of those ephemeral streams of liquid water, microbial life has managed to arise. We will have to wait for future rovers and explorers to confirm this hypothesis. What will really change our understanding of the Red Planet are the NASA and ECA missions, both part of the Mars exploration program. Since 2007, the main goal of space missions to Mars was not just to follow the water, whether in the form of ice or liquid water, but to explore its habitability, and above all, to seek signs of life.
The more we investigate Mars, we obtain more clues that the ancient history of Mars was certainly supportive of life, and then that final step of, did life actually evolve? And then if it did, where did it evolve? And what clues are remaining today? Because that was so long ago.
The ultimate aim of missions to Mars is to prepare for human exploration, a step that would really be a new milestone for mankind. The first step in this ambitious exploration program is the ExoMars program, a partnership between ESA and Russia's Federal Space Agency, Roscosmos, with the participation of NASA. Its primary scientific goal will be to search for possible biosignatures on Mars, past or present. ExoMars is a multi-spacecraft program. The first ExoMars mission, ExoMars 2016, is called the Trace Gas Orbiter, TGO. The goal of this orbiter is to study the Martian atmosphere for the presence of methane and other gases. Gases that might be linked to some biological processes. The second mission in the ExoMars program is the 2018 ExoMars rover and landing platform. The ExoMars rover is a rover with a 2 meters core drill to sample various depths beneath the surface where liquid water may be found.
The drill was supposed to penetrate the first couple of meters within the sediments. This way is more probable maybe finding evidence of viable salts.
The third step of this enthralling Mars exploration program is the NASA mission, Mars 2020. The aim of the Mars 2020 rover is to study diverse rocks and soils to understand past habitable conditions on Mars and to seek signs of ancient microbial life. One of its functions is to monitor weather and dust in the Martian atmosphere and test the ability to extract oxygen from the red planet's carbon dioxide atmosphere to prepare for future human exploration. Any of these breakthrough missions might solve the enigma of whether there is past or present evidence of life on Mars. Much further away than Mars, there is another unique world that might harbor life. Our next destination in the search for life is one of the most fascinating Jovian moons, Europa. Europa is one of the 4 largest moons of Jupiter. It's slightly smaller than our moon, and its icy surface is minus 160 degrees Celsius. Virtually everything we know about Europa is thanks to NASA's unmanned space probe Galileo, which passed by Europa 12 times. These were the first images it captured. It is covered by a smooth layer of water ice. In fact, it has the smoothest surface of any known solid object in the solar system.
The surface of Europa is unique in the solar system. It has very few craters, which tells us that the surface is being reprocessed frequently.
Some parts of its surface show blocks of ice that are separated but seem to fit together like a puzzle. These icebergs could have been shifted by slushy or liquid water beneath.
These cracks probably may extend all the way down to the ocean, to the ocean, or at some point, so you could get some percolation of water.
This peculiar landscape is very similar to sea ice on Earth.
Galileo was able to detect that. All of those things together add up to our picture of how we now know that Europa has a liquid ocean under its surface.
In 1996, the Galileo spacecraft detected a magnetic field on the planet's surface, indicating that there must be some electrical conduction likely to derive from a salty ocean that could be 60 miles deep.
The studies and observations, measurements that have been made in the past decades seems to be converging pretty clearly with the presence of an ocean under the surface of the ice.
So there we have the first key ingredient for life, liquid water. How can water remain liquid at temperatures of minus 160 degrees Celsius? Some sort of mysterious internal heat must be melting the icy crust. Jupiter is the key. Tidal heating from friction due to Europa's eccentric orbit around Jupiter has been proposed.
The ice at the surface of Europa is being cracked. It's not completely sealed. You can see because of gravitational pull and pull, there is this tug of war as Europa is moving around Jupiter. You can imagine that all this friction is creating lots of energy, lots of heat, and then we have good reasons to think that there are hydrothermal system, which means that you have, water being heated by this process.
Volcanoes deep down may harbor hydrothermal vents that provide an energy source to heat and maintain liquid water. So we have two of the three conditions for life: a liquid, in this case liquid water, and a source of energy, that interior heat. We would just need some organic compound, and the chances of life arising would skyrocket. The Galileo spacecraft observed that Europa's ice contains carbon dioxide. When this carbon dioxide is strongly impacted by Jupiter's radiation, it can produce simple organic molecules such as formaldehyde that are steps towards life. The aforementioned tides on Europa could also mix life-supporting substances together in the ocean, but nothing has been proven yet. On 2013, NASA reported a surprising discovery on the icy crust of Europa. Some clay-like materials, specifically phyllosilicates, were detected.
Phyllosilicate just means phyllo, like layered silicate, and these are a fancy name for clays. And clays are a kind of mineral that forms in a lot of water. And on Earth, there are some theories that these clays were some of the original minerals that were present when life was evolving.
According to some hypotheses, the presence of these organic associated minerals may have been the result of a collision with an asteroid or comet. With liquid water, an energy source and the necessary chemical building blocks, perhaps delivered by comets or asteroids, Europa opens up the possibility that life could exist in places never imagined. "12,000 feet beneath the Arctic ice sheets, in complete darkness, there are hydrothermal vents that spew out superheated water with lots of toxic chemicals. Scientists think vents like this could also exist on Europa's ocean floors.
We think that the potentially source of energy for an ocean Europa will be the volcanic activity.
We have recently discovered that clustered around the vents, there are extremophile microorganisms that cover miles of the Arctic seafloor. The discovery of life there really raises the possibility of life on Europa.
Probably Europa might be the best candidate for us to find extant life.
The challenge now is to prove that life has been able to thrive in such a bizarre environment. NASA and ESA have planned 2 different missions to Europa that will investigate its habitability in the next few years.
In 2015, NASA approved a new mission to go to Europa and investigate its environment, and particularly to look for habitability.
NASA's Europa Multiple Flyby mission is a spacecraft that will be launched in the 2020s. The spacecraft will be a highly capable, radiation-tolerant probe that will perform repeated close flybys of the icy moon.
We'll also be looking under the surface to learn more about the structure of the ice shell and the structure of the ocean underneath the shell, using radar and magnetic field detectors and other instruments.
The ESA is developing in parallel its own mission, the Jupiter Icy Moon Explorer, the so-called JUICE mission, that is planned for launch in 2022 and arrival at Jupiter in 2030. This spacecraft will spend at least 3 years making detailed observations, not just of Europa, but also of the giant gaseous planet Jupiter and 2 of its largest moons, Ganymede and Callisto. We will have to wait till the next decade to confirm whether or not there is life on Europa. Europa isn't the only intriguing place this far out in the solar system. Could similar conditions exist on other moons orbiting other planets, even further away from the Sun? Orbiting Saturn, there is a small, mysterious moon that is totally different from the rest of its more than 60 moons. This tiny icy moon, only 300 miles across, is Enceladus. In the last few years, this tiny moon has become the main goal for exobiology, as it has revealed some extraordinary conditions for harboring life.
Most of what we know about Enceladus is thanks to a mission called Cassini. It's a mission that it's been going on for many years. It's an orbiter that has been studying the entire Saturn system and its different moons, but it's been paying close attention to Enceladus.
The Cassini mission offered us a close-up of this remote world for the first time ever. These were the first images it took. The surface is white and glittering, and it is carved with fissures, crests, and cracks. At the South Pole, Cassini made a surprising discovery. It photographed some strange, large cracks, seen here in blue. 4 parallel fissures, scientists named the tiger stripes. They are 75 miles long and hundreds of feet deep. They are similar to fault lines on Earth. After several flybys, Cassini's thermal radar revealed something unexpected. The tiger stripes should be colder than the rest of the moon, as they were in the South Pole. However, they were radiating heat. The fissures were at minus 80 degrees Celsius, which was more than 120 degrees Celsius warmer than the rest of the moon.
It's definitely a place where we see evidence that something profound is happening in terms of potential for habitable environment.
But the most shocking finding was still to come. When Cassini was reoriented, it captured a shocking image. Vast jets of ice were erupting into space.
The camera was able to image plumes of water vapor and ice crystals coming off the south pole of Enceladus.
These actual images showed the plumes were ejecting ice particles hundreds of miles out from the tiger stripes.
Those materials are being ejected through fractures on the surface of the moon, which seem to be connecting the surface with the interior.
However, how this small moon can generate so much heat as to be able to maintain such geothermal activity? Scientists believe that Enceladus might have an internal energy source, like Europa. When it orbits the massive Saturn, friction from gravitational process causes it to heat up, melting ice in the moon's interior in the same way as on Europa. These jets were giant geysers of water that erupted from its icy surface, much like those in geological hotspots on Earth.
Cassini actually has a detector that can fly through the plume, pick up some of the particles and analyze them chemically. And when that detector did its work, it found that some of the particles are salty. And the only way to get salt incorporated into a particle is to have it evaporating directly off of liquid. So that was yet another hint that Enceladus has liquid under the surface from which these plumes are emanating.
But could it prove that under the icy crust of Enceladus existed a subsurface ocean, like on Europa?
We needed even more evidence. The next piece of evidence was from Cassini flying past Enceladus and just carefully analyzing its trajectory as it flew past Enceladus to directly measure how Enceladus's gravity was pulling on the spacecraft. And when that analysis was done, it found a density anomaly under the entire South Pole, indicating that you have a regional sea of water from which these plumes are emanating.
These jets might be connected to active hydrothermal vents at a subsurface water ocean floor, where the moon's ocean meets the underlying rock, a prime potential habitat for life. But there still wasn't anything that could prove life existed underneath that icy crust. The probe spectrometers detected something really exciting. They found in the jets the basic chemical building blocks of life.
So Enceladus is fascinating because, as far as we can tell, it contains the three basic ingredients for life: liquid water, nutrients, and organics.
But does this strange and alien world actually support life? The geysers could provide easy access for sampling the moon's subsurface ocean. And if there's microbial life in it, ice particles from the sea could contain the evidence astrobiologists need to identify them. There are 2 exploration missions proposed by NASA to Enceladus in the near future that would try to find evidence of life in the tiny icy moon. The first one is the Journey to Enceladus and Titan mission. This is an astrobiology mission concept to assess the habitability potential of Enceladus and Titan, moons of Saturn. The second mission, waiting for approval and financing, is the Life Investigation for Enceladus. This proposed mission would capture icy particles from Saturn's moon, Enceladus, and return them to Earth, where they could be studied in detail for signs of life, such as biomolecules.
It's relatively simple, technologically speaking, to send an orbiter to Enceladus that can capture those icy particles in the plume and analyze them in situ or bring them back to Earth for detailed analysis in the laboratory.
Unfortunately, none of these missions have been approved yet. So we will still have to wait to unveil whether or not there is life on this tiny, enthralling moon of Saturn. Close to Enceladus, there is the last of the great candidates for life in the solar system, Titan.
Titan is the largest moon of Saturn. It is one of the largest moons in the solar system, and it is also the only moon that is known to have a thick atmosphere.
Data from the Cassini-Huygens mission, which flew by Titan in 2004, demonstrated the existence of hydrocarbon lakes.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water.
In these seas and lakes, there are no waves, as the liquid is liquid methane and ethane, which is much less dense than water liquid. These 2 hydrocarbons on Earth are volatile gases. But on Titan's minus 180 degrees Celsius temperature, they are liquid. Titan has a very similar landscape to Earth. There are seas, lakes, smoothed rocks on the riverbeds, mountains, valleys, canyons. But these mountains and pebbles are not made by any rock like on the Earth, but they are made of water ice, so frozen due to the minus 180 degrees Celsius temperature on Titan's chilly surface that it behaves like rock. Cassini's radar images showed that on Titan, liquid methane forms clouds, thunderstorms, and even falls as rain.
Methane in the atmosphere also plays a role similar to water in the atmosphere. On Earth, you have a water cycle. On Titan, methane plays a very similar role. It falls to the surface as rain or mist. We do see channels and rivers where methane is flowing across the surface and doing geological work like we would see water do on the surface of the Earth.
Liquid methane has a cycle very similar to Earth's water cycle. The question is, could it behave like water does on Earth, as a liquid that allows organic molecules to dissolve and interact? There is no easy answer to this. Titan's atmosphere also contains many organic gases, such as methane, ethane, and hydrocarbons, and possesses conditions that resemble those of early Earth 4 billion years ago that allowed life to develop.
In many ways, the atmosphere of Titan looks like a young Earth in the fridge, much colder, much cooler. But prebiotic chemistry, the same processes are there. What we don't know is whether these prebiotic processes are turning into something that is biological in nature at the surface of Titan or in the subsurface.
However, liquid methane and ethane are much colder than liquid water by some 200 degrees Celsius, and biochemical reactions would occur at painstakingly slow rates. These compounds are also far less capable as solvents compared to water, and therefore much less life-inducing. Water is also missing from the picture due to freezing temperatures of minus 178 degrees Celsius. Several experiments have shown that with an atmosphere similar to that of Titan and the addition of UV radiation, complex molecules and polymer substances like tholins can be generated, substances that could be considered a sort of precursor to life.
What weirdo chemistry, physics, biology could be. People are trying to think in terms of what could be a biology based on methane. It's not the best, apparently, when it comes to provide a structure for biochemistry.
The conclusion is that Titan is a world rich in organic matter, with a methane cycle comparable in atmospheric and geological processes to Earth's water cycle, that is really likely to harbor life. In the last years, NASA and ESA have combined efforts to develop an unmanned space mission that could finally unveil all the Titan's mysteries, but none of them have been approved yet. One of the most exciting missions proposed to unveil the secrets of the methane and ethane lakes of Titan is NASA's Titan submarine. This submarine would explore the depths of the Kraken Mare, the largest known body of liquid on the surface. This mission would be designed to measure the organic constituents on Titan and would have performed the first nautical exploration of an extraterrestrial sea, analyze its nature, and possibly observe its shoreline. As the other proposed mission to Titan, this Titan submarine mission hasn't been given the green light yet.
There's lots of really fun options for exploring Titan, but NASA has not actually selected one of these options.
Therefore, to date, there are no confirmed space missions to Titan in the coming years. But everything could change if a shocking discovery is made in the near future. Whether or not any of these potential space missions finally reveal the existence of life on Mars, Europa, Enceladus, Titan is an unknown. But what we do know is that now we are much closer than ever to finally finding an answer to the question of whether there is life beyond Earth. 50 years ago, the era of robotic exploration of our solar system was just beginning. In July 1965, the Mariner 4 probe sent the first close-up images of Mars. Those blurred images showed that Mars did not have vegetation, much less canals crisscrossing the planet, as envisioned by earlier generations of astronomers. At that time, the most widespread opinion was that Mars was not just the red planet, but also the dead planet, with the chances for life of any kind being considered infinitesimal. Things have radically changed since 1965, thanks to the extraordinary advances of technology that have led us to use more and more sophisticated space probes to explore our neighbors in the solar system. The three vital factors, energy, liquids, and chemical building blocks, are more widespread than has ever been realized. Now it's not so unlikely to find life beyond the Earth in our solar system. We can't deny that such a huge discovery, even if it were just microbial life, would be really shocking for mankind, as it would imply the first step toward believing that we may not be totally alone in the universe. Then, the right conditions could also exist beyond the boundaries of our own solar system, in distant outer space.